Okay, should I get started?
Sure.
So we called this, what did we call this? How to, let me start making some, yeah, okay, fine. So lean, right? This is the interactive theorem prover. I think for 15 minutes, I'm just going to show you what it looks like and feels like to use this system. We'll prove a very, very basic theorem, and then we can talk about the potential consequences of the fact that this technology is becoming somewhat usable for a mathematician. Okay, so first is how you would do what I'm doing right now. This is inside a web server. You go to github.com and you get an account. It's free. You just click a button. Okay, you need something for github.com. Step 2 is you Google Mathlib 4, and the first hit will be the main Mathlib website.
This is me. I'm trying.
But it's working on the other screen.
It's working on this, yeah. Okay, there we go. So now you can see. You don't need to see this. I'm just showing you how you would get to the screen that I'm actually trying to get to if you wanted to repeat this experiment. So you Google Mathlib 4. This is the first website that comes up. You click that link, and it takes you to this crazy looking thing. Okay, this, as a mathematician, like I can't tell anything that's going on here. Ignore everything. Scroll all the way down, and it says installation, but actually we're not going to install anything. We're just going to play in the in the web. And there's something called open in GitHub codespaces. So you click that button, and after like 5 or 7 minutes, it'll take you to something that looks like this. I've blown it up so that you can can you see in the back? I guess you have that one to look at. It's big enough. So let me right away get rid of this screen and I'm about to get rid of this screen. I made a new file, brand new file called ias.lean so that we can play around. This, what codespaces opens up is the entire Mathlib library. Maybe we'll talk more about what that is, but let's first just see the software in action. So I'm going to get rid of that. And now we have Mathlib. So how to use lean. The first thing I did is I wrote import Mathlib, which says load everything that Mathlib has in it. So Mathlib is the math library of lean. Lean is software that we're going to see in action. I mean, that's what's being run right now in the web. And on top of that software, mathematicians have built a library, and I've imported everything in the library, including the real numbers, including all kinds of stuff. So let's just do we're going to take 10 minutes and prove a very, very basic theorem. Anybody have like a favorite? How about the squeeze theorem? That's nice and easy. The squeeze theorem is something. So first, let's define what it means to be a sequence. So a sequence is a map. Well, what does it mean for a sequence to converge? A sequence is just a map from the natural numbers, let's say, to the real numbers. So let's define what it means for converge. Sequence converges to. And so we'll need a sequence, let's say an. So an is a function from the naturals to the reals. This is big enough for you to see. Okay, so that's a sequence. What does it converge to? Let's say it converges to a limit L. So we're given, if this is a definition, we call the definition sequence converges to. Our assumptions are a sequence A, which is a function from the naturals to the reals, and the proposed limit, which is a real number L. And we're going to, does an converge to L or not is a proposition. It's a true or false statement. And how do we determine if an converges to L or not? For all epsilon. So if it's true that for all epsilon positive, there exists natural number n. Now I don't even have to specify that n is a natural number or that epsilon is a real number. You'll see in a second why. So that what holds? So that for all little n greater than n, we've had enough wine. We know how to do this. An minus L is bounded by epsilon. Yeah, so the sub n is how we would write it in human language, and in the computer language, a is a function whose input is a natural number n. So we write a. You can put the parentheses there if that if that makes you feel better. There are slightly fewer characters if you don't put the parentheses there, so you don't actually need the parentheses. So we'll just say a space n is that we've gotten this real number, and an minus L is less than. So, question. The commas are syntactical. Yeah, you need the commas. So that's what it means for a sequence to converge. And now let's prove the squeeze theorem. So we'll prove a theorem. We'll call it the squeeze theorem. Squeeze, we could call it Bob, it doesn't matter. We're just making up a name. What's the squeeze theorem? We have three sequences. Let's say A, B, C. So A and B and C are all sequences. They're functions from the natural numbers to the reals. We'll have a number L. We'll have the fact that, let's see, how do you want to do this? B will be the one in the middle, and A will be a lower bound, and C will be an upper bound. So we have a hypothesis. Let's have a hypothesis. What should we call the hypothesis? It's that A is less than or equal to B. That's just the name for the hypothesis. The hypothesis would be, the actual assumption is that A is less than or equal to B. And Lean knows that this means for all n, A of n is less than or equal to B of n. We'll also have another hypothesis, B less than or equal to C, which is B is less than or equal to C. Okay, so A is squeezed between B and C. Let's have the hypothesis that that A goes to L. So A goes to L is the fact that, so how did we call this? We called it sequence converges to, I wish I had chosen a shorter name, but too late, AL. So sequence converges to has two inputs. It's a function that takes in two inputs. One is a sequence, a function from the naturals to the reals, and two is this real number L. And it's a prop, it's true, false. So we're assuming that it's true that A converges to L. So far, so good. Similarly, we'll assume that C converges to L. And then what do we have to prove? So these were all our assumptions. And finally, we have a colon that says, given all these assumptions, the thing that we're actually going to prove, it doesn't need to have a name because it's the thing that we want to prove. We want to prove that B, therefore, converges to L. Okay, and then we're going to start the proof. So this is the best part of Lean. The best part of Lean is that on the right, we haven't talked about the right-hand side at all. The left-hand side is me talking to Lean. The right-hand side is Lean talking back to me and telling me what it understands. So what it understands right now, so this is the beginning of the proof. The colon equals by is the beginning of the proof. And what it understands when I put my cursor right here is that what stage of the proof are we in? We're in the following stage. We know that A, B, and C are functions from the naturals to the reals, that is sequences. We know that L is a real number. We know that A is less than or equal to B. We know that B is less than or equal to C. We know that A goes to L and C goes to L. And this symbol means the goal. What are we trying to prove? Our claim is that B converges to L. So far, so good. So this is the interactive theorem prover. It talks back to you as you try to talk to it. Okay, so what's the first step in the proof? Well, if you're teaching like undergraduate real analysis, you say, well, guys, what was the definition of a sequence converging? So let's remember what the definition is. That's called unfold. So let's unfold the definition of seq converges to. So remind me what seq. So if I put the cursor back at line 15, it still has the original state. This was the original goal state. And when I go to the end of line 15, or just go to line 16, the goal state has changed. And all it did is, now this unfolding is, Lean doesn't need the unfolding. I need the unfolding because I'm a human being and I forgot what the definition is. Lean knows what the definition is. In a second, we'll comment out that line. It changed the goal state to a definitionally equivalent goal state, because that's how we defined sequential convergence, to say for all epsilon, there exists an n, yada, yada. It didn't change anything else, yeah. So that, because all we did is we told it to unfold on the goal. Now, we can also unfold at one of the hypotheses if we want to remember what A to L means. So let's do the same thing. We'll unfold this at A goes to L. And now it's done, get out of the way, go away. Yeah, now it's done the unfolding here as well. But it didn't do it at C goes to L, still says sequence converges. Okay, so you completely interact with it. You have to tell it what the proof is, and it keeps track and says, I've understood what you said or not. So far, so good. Okay, so again, think back, you're teaching intro real analysis. So, okay, good. Everybody remembers what it means to converge. It's that for all epsilon, there exists an n. So what's the first thing we should do? Yeah, give me an epsilon, right? You're saying for all epsilon, something's true. So give me an epsilon. So let's introduce an epsilon and the fact that epsilon is positive. So that's called intro. So if we introduce an epsilon, if we just introduce an epsilon, that says the new goal state is that there is some epsilon. And then if epsilon's positive, then we have to prove something. If epsilon's not positive, there's nothing to prove. Okay, so we've introduced epsilon. Let's introduce also the fact that epsilon is positive. Let's call that epspos. Just, I like to name my hypotheses by what things are. So you'll see a lot of people call it H1, H2, hypothesis 1, hypothesis 2. Then you have to remember which hypothesis which. Of course, you can look here and tell which one is which. I like to just name them by what they say so that I don't have to remember anything. I'm too dumb to remember things. So intro epsilon and epspos means we have two more things in our list of assumptions, that there is an epsilon and that it's positive. And now our goal state has changed to there exists an n, so that for all n greater than capital N, we have this inequality. So far, so good. Yes, Jordan. Oh, it's that. So if I just, so let's go to the beginning of the line. The beginning of the line before I introduced epsilon, and by the way, so it keeps track of everything. As I move the cursor, it changes the goal state and it remembers all the possible goal states as we go along. So we started with unfolding, and now before we introduced epsilon, the statement was for all epsilon greater than 0, but that's secretly packaging two things. First, you have to give me a real number epsilon, and then you have to give me the fact that epsilon is positive. And those are separate things. No, we can call this Bob. So that's right. So right now I've introduced Bob, but not the fact that Bob is positive. And so the goal state says if Bob is positive, then we have to prove something. So then we can intro Bob positive. And now we know that Bob is positive, and now we have to prove that there exists an n. Does that make sense? Yeah. Yeah. So right here it says for all epsilon greater than 0. So the fact that the first thing in this goal is for all says, okay, so I have to give you something for us to make progress. That's what the intro, these are called tactics. So intro is a tactic that if it sees for all, like if I tried to intro somewhere else, we don't have somewhere else yet to work with. But if I just say intro, if I actually right here, the next step is not something that I can intro. The next thing that we have to do is there exists an n. It wants us to provide an n. If I say intro n, it'll say the tactic failed. I don't have anything to intro. Okay, so the fact that there are no error messages is that it understood what I said. The goal is for all epsilon positive, so give me an epsilon. We'll call it Bob. Can we go back to calling it epsilon? Yeah, thank you. Yeah, it does. Yeah, that's right. We can be, there's nothing magical. I just made it a name. We can be very perverse and call epsilon neg the fact that epsilon is positive. Yeah. So it's up to us to call it whatever we want to call it. So there's nothing special in the names. So if you wanted to introduce another constant, that's a let. So let nu be epsilon squared, if you wanted to do that, epsilon squared. So now we have nu, which is a real number, which is defined as epsilon squared. So that's not an intro because it's not a tactic that's working on the goal state. So there's all kinds of different things that you can do as you'll learn how to use these things.
Some natural syntax like we just not like epsilon squared, but there's also some other that epsilon underscore pos means something.
It's just epsilon underscore pos is just the name. Yeah. Yeah, because if you look at what this is of the form P implies Q. If epsilon's positive, then we have to prove something. That's what we're trying to prove. Yes. It's because in the definition assumes that epsilon is positive. That's, yes, it's unfolding the definition. So right here, we unfolded the definition. We didn't actually need, so if I comment out this unfold line, nothing will change because lean knows that sequence converges means for all epsilon. So it doesn't actually, that's just for us as humans to be able to remember what the definition is, but lean will still know what the definition is. And then Sure.
the reason intro epsilon, if you just essentially define this object, but you then gave an attribute of being positive, where did that happen?
It's right here. It's that the goal, our goal is to prove that for all epsilon positive, something happens. So it's based on the goal. It's absolutely based. It's essential that it's in the goal. We have to prove this. Yeah. Yeah. So so once we are given an epsilon, we have to know that that epsilon is positive. Otherwise, there's nothing to prove. So now give me the fact that epsilon is positive. Let's keep nu around. Nu's not hurting anybody. Okay, so we have to get an n. Where are we supposed to get this n from? From the other ones, yeah. So I don't know what n we're gonna need. So let's let n be a natural number. And sorry, I don't know what it is yet. Okay.
Sorry, a keyword?
Sorry is a keyword that says I'm supposed to provide you a proof or a construction, or I'm supposed to give you instructions, and I'm sorry I'm not going to, but don't give me an error message. Okay. So right now we have a natural number n, which I don't know what it is, and we'll figure out later what it is. I'll provide the construction of n later. So the fact that it says there exists an n, so that for all little n something is true, well, let's say this is the capital N that we want to use. So we'll say use this capital N. And now it's changed. The goal state has changed to, okay, so we have this capital N. I said the question before the use was there exists some capital N with some property. I told it which capital N to use, even though I didn't actually specify what that say I had some capital N that was a natural number, then we would be able to continue the proof. So let's use that capital N. Then we would have to prove that for all little n greater than capital N, something else happens. So what should we do? Intro, because it's a for all little n. So intro little n. That says if little n is greater than capital N. So let's intro the fact, give me the fact that little n is indeed greater than. So intro n greater than capital N. So there is, and that's just called intro. The problem with just intro by itself is that you have to name the variables. This is like, it's going to give you something, but it's something that you can't access. So you have to say what you want to call the variable. You can call it whatever you want. It doesn't have to be little n. I'm not sure. Yeah. So if it satisfies a whole bunch of things, depending on how things are packaged, you can just say n properties, and then it'll give you all of them. But if there really are 100 different things that n has to satisfy, you might want to have access to all. It probably satisfies those things because you want it to satisfy those things, meaning you want to have access to it, meaning you want to have a name. You want to be able to call it something. Does that make sense? Yeah, I can call it n property or something. It doesn't matter what I call it. I misspelled property. It's whatever I call it is what it will be called, but the fact is still n greater than capital N. I can't the meaning I have no control over because there's a theorem with content. The name for that fact I can call whatever I want. True or false? Yeah. Go ahead. It's like equation number. Yeah, exactly. This is equation number. This is equation 13.2. It won't let me. 13.2. Yeah, equation 13.2 is the fact that n is greater than. Sam, did you have more? No. Does that make sense? So I'm just giving it a name, but I like to give it names that are, because I can't remember what I named something. I don't know what 13.2 is. So I'll give it the name which mimics what its meaning is. And maybe that's confusing to give it the same name as the meaning. Spelled?
It's misspelled.
Oh, misspelled more often. Okay. Right. The keywords, here's the easy thing. The keywords are the blue. The things that are highlighted in blue are keywords. It's black. Oh, well, it's on my screen, it looks black, but I think you're right. It's very dark blue. This is not a colorblind friendly environment. Yeah, I'm sorry. You can probably change the configuration. Yeah. Okay. Yeah, go ahead. Yeah, sorry's in red. Sorry's in red because it's a special kind of tactic that's different than the other kind. Yeah. Correct. Yeah. And it's not going to let me continue the, I mean, at some point I'm going to have to fix the fact that there's a sorry there. Okay. So far so good. And little n is greater than capital N. And now I want to prove that the absolute value of Bn minus L is less than epsilon. Of course, the way that if you think about the proof, An is coming in from below, Cn is coming in from above. And so Bn is going to get squeezed between them. So the reason the absolute value is less than epsilon is because there's a lower bound because of A and there's an upper bound because of C. So really what I want to do is break up the fact that Bn is less than, Bn minus L is less, in absolute value less than epsilon. That's really two things that I want to prove, that there's an upper bound and a lower bound. And we're going to have to prove those separately because they come from different reasons. So what's that? So let's open something like, I don't know, Grok, or what's your favorite LLM? Gemini? I shouldn't be trying this live. Let's try Gemini. Gemini. In Mathlib 4, how do I convert absolute value is, absolute value less than something, absolute value less than something into two inequalities? And I misspelled a word, it doesn't matter. Okay, so they say it's called abs LT. Let's see, can I make this big enough that you can see? It's called abs LT. Now, so take your favorite AI, it's going to hallucinate the name of a theorem that doesn't exist. So what I always do is when it suggests the name of a theorem, that's good. Let's check if it's real. So we'll go to Mathlib for documents, docs. So here's the documentation for Mathlib 4. And I copied the theorem that it said abs LT, which by the way, smells like the right name for the theorem about absolute values and having a less than sign. Let's see what that theorem actually says. So here it is. It does occur. And the theorem name is that, let me click it again, since it ran away from me when I was zooming in. Okay, there we are. So it says that in any additive group with a linear order and additive left mono and add right mono, whatever, yada, yada, because it has to be so general, it's not just going to be a fact about real numbers. It's going to be a fact about any situation to which this could possibly apply. And it says that the absolute value of A is less than B if and only if A is greater than negative B and A is less than B. Now, you don't see greater than signs and less than signs. You only see less than signs because that's a greater than sign has different meaning than a less than sign. And the fewer different kinds of things you have, the less the AI that's going to be searching for theorem names has to think. So in Mathlib, you just exclusively use less than signs and always, almost exclusively. I'm about to break my own convention because right there is a greater than sign. But actually, that's an abbreviation for B is less than A. So, but try to use less than signs. Okay, whatever. There's a convention. So this is the theorem that I want to use. I want to turn the statement that absolute value of something is strictly less than something else into a pair of statements. So that has a name. The name for that is rewrite. Let's rewrite this theorem. So that's abbreviated to RW. Rewrite the theorem, which was called abs LT. So this is one place where if you don't know what that theorem is, you have to go find it. And there's a variety of ways to find it. LLMs are actually pretty good at, if you just describe in natural language what kind of theorem you're looking for, it's probably in the library. The library is pretty good these days. And it'll find it for you if you want to double check that it really is doing what it's supposed to. You can either just try it directly in Lean and see if Lean takes it, or you can go to the documentation and see if that makes sense. Okay, so look at what happened. Our goal was to prove that the absolute value is less than epsilon. And after we write by this, the goal is two things, a lower bound and an upper bound. So far, so good? Okay, so so there's a tactic called when you have to prove two things, you actually have to prove something, comma, something else. And it's in curly bracket, not curly, what are these called? Angle, yeah, angle, thank you, angle brackets. So what I don't know how to prove either of those things. So let's do refine, and it's going to be angle bracket something else, angle bracket. Well, let me sorry out the first one. We know that sorry is good. And well, I don't know what the second one's going to be. I see. Is it going to complain? No. Yeah. So I don't know what the first bound is. There's some proof that the lower bound is going to be okay, but let's worry about the upper bound. Okay. How are we going to prove that Bn minus L is less than epsilon if little n is greater than capital N? We have to get that upper bound from somewhere. Because C, with that value of epsilon, so let's remember, let's have the fact that C, what was it called? C goes to L, right? C goes to L. So I didn't give this fact a name, and the generic name for a fact that you don't name is this. So I'm just going to call it nothing, and that means Lean will call it this. And we have the fact that C converges to L. Now, C converging to L is actually a function. It's a function that takes an epsilon, the fact that epsilon is positive, and returns capital N. So let's feed into this the epsilon that we have. Okay, so now this has turned into, if you can prove for me that epsilon is positive, then I'll have some capital N for you. Right? So if I give it epsilon, the fact that epsilon is positive, now I have this capital N. Oh, in fact, I should have gotten that capital N before because I'm going to need that capital N in the construction of the true capital N. So let me move this have to before we started constructing capital N. Okay, so all the way back here, we know that there exists some capital N so that this holds. So the fact that it exists is great, but I actually want it. I want you to give it to me. I want to obtain the capital N and the property of capital N. So that's called obtain. So instead of a have, what I really want to do, instead of just have means I'm declaring a statement. Just like let means I'm defining something. I'm defining this thing new out of nowhere, which is called epsilon squared. And Lean says, sure, go ahead. So have is I'm going to make a statement, and that statement is that that I have C2 to L with this epsilon, and the fact that epsilon is positive tells me that there exists some capital N. So let's obtain that capital N. There's like an N1, which is the lower bound, and an N2 that's the upper bound. So let's obtain this pair of things. So again, combinations of things go in angle brackets. We'll call this capital N2. And then the hypothesis on capital N2, I'm just going to call HN2. I'm not going to give it a descriptive name since descriptive names seem to upset you guys. So we now have a capital N2 and the hypothesis on N2, which is that as long as little n is greater than N2, little cn is at most epsilon. So far, so good? So whatever this capital N will be, let's have the fact. This time I will give it a name. Let's see. N2 is less than or equal to capital N. So what is the fact? It's that N2 is less than or equal to capital N. And the proof, well, I can't prove it until I specify what capital N is. Of course, capital N will be the maximum of N1 and N2. Right? We don't have to have a lot of, what's the word I'm looking for? There's not a lot of suspense in how this proof goes, right? Let's in fact do it right now. So let's obtain N1 and the hypothesis on N1, which is that A goes to L with that same value of epsilon. And then what is our capital N? The max of N1 and thank you, and N2. So far, so good? So we got this N1 with the fact that AN is going to be within epsilon of L. Once you're past N1, we got an N2. Capital N is the maximum. Now we can fill in this proof. So if I go here, look at what happened. I claimed that there was there's this fact. I'm going to call the fact N2 less than or equal to N. And the proof is Well, now we're inside the have. So it's forgotten about the rest of the proof. Now our goal has just become n2 is less than or equal to n. I was supposed to finish a few minutes ago. So let me just say one last thing, and then we'll stop and we can just have a philosophical discussion about what all this means. I think you're getting the point about how this works. So how do you prove this? I don't know how to prove this. Let's see if the AI can find it for me. So that there's something called, let's try to apply a theorem, but I don't know which theorem. So I'm going to do apply question mark, which says try to find a theorem that will do it. And it's right here. It's exact AN1. That's not right. So let's try again. This takes a little bit longer because I'm using the web browser version instead of running it on my computer. Okay, so it's right here. The theorem is called nat.le max right. So the maximum of two things is not less than either of those things. In this case, I want the one on the right, whatever. But the AI found the proof of this theorem for us. And now when we go down to here, we're now in the point where we want to prove that B minus L is at most epsilon. We're going to use that. We know that little n is greater than this little n is greater than n2. And together with this inequality, you can finish the proof. I think I've sort of demonstrated the basics of how to use this technology, and you're more than welcome to play with it on your own, and we can just talk.